Hi everyone, I am Sayam Galotra. Today I am going to present DataPrism, a system to expose disconnect between data and system. This is joint work with Anna from Microsoft, Rauni and Juliana from NYU, Alexandra from UMass, and Devesh from AT&T. Data-based decision-making systems are widely being used in real-world applications spanning natural language processing, healthcare, stock prediction, and many others. The increased usage of such systems has been possible due to the recent advancements of deep learning. It has become extremely easy to develop such systems because of easy access to large amounts of data from various repositories like Google Dataset Search, data.gov, and so on. On the implementation side of things, ML libraries have made it simple to code these applications in less than 500 lines of code, which traditionally required 500,000 lines of code. This is all great, but one of the common challenges faced in the development is that the pipeline has some specific assumptions or expectations which the dataset does not satisfy. This mismatch of assumptions and reality causes the system to crash or have poor performance. We refer to this deteriorated performance as malfunction. Now, let us look at an example. Suppose you have built a health monitoring and recommendation system in the United States. It is doing really well because it demonstrated highly accurate results. Now, you get a chance to collaborate with a hospital in Australia, and when you deploy the algorithm, it achieves embarrassingly low accuracy. Now you are confused to see such a stark difference in the performance of the system. After a close investigation, you notice that all individuals are entering their weight in kilograms, which is causing this problem. The software, which was designed in the US, was assuming that all individuals enter weight in pounds. The moment you change the units of weight in the Australian dataset to pounds, the accuracy improves to over 0.9. In this case, neither the data was wrong, nor the system was wrong, but there was a mismatch between the system's expectations and the input dataset. Now, let us look at another example of malfunction. In this case, you train an ML model to predict income of individuals and ensure that it does not discriminate against sex. Now, when you use the same pipeline to train it on another dataset, it is highly biased against women. After a close investigation, you observe that there are two main causes of bias. First, more male individuals have higher salary than female individuals. Second, females with higher income are fewer in the dataset, because of which the system tends to ignore those individuals. After seeing these two examples, now let us try to see how we can explain such mismatch between data and systems. For this purpose, we define a PVT, which is a tuple of three components: data profile, violation function, and transformation function, and hence the name PVT. First, a profile is a data property which is satisfied by the tuples. For example, given this data set, the domain profile of marital status is the set married and unmarried. Similarly, correlation data profile of sex and income shows the correlation of columns is 0.63. In addition to a profile, a PVT consists of a violation function which characterizes the violation of any input dataset with respect to the profile. The violation score is considered to be within the range 0 to 1. In this example, one tuple out of the 4 does not satisfy the input domain of married or unmarried. Therefore, the violation score is 1 by 4. Third, a PVT consists of a transformation function which modifies the data set to reduce the violation. For example, if you want to change the domain of income column to 0 and 1, then this transformation can be applied. We use PVTs as a key ingredient to explain the cause of malfunction. And in order to identify the set of PVTs that are the cause of this malfunction, we take an interventional approach. What we mean by this is that we forcefully modify the input dataset and then evaluate its effect on the performance of the downstream task. Let us look at an example of an intervention. We start with the same dataset we saw in the previous example. Now, we transform this dataset according to, say, two different PVTs. First, we impute the missing values in the age column, and second, we transform the income column to 0 and 1. Now, after this transformation, we evaluate the malfunction of the model with respect to this new dataset. This malfunction value confirms whether the changes performed in the original dataset help to reduce malfunction or not. Now that we have understood what profiles and PVTs are, let us look at the problem setup. We are given two datasets, one of which is a passing dataset. That is, it performs well with respect to the system implementation. And the other one is a failing dataset, which does not work well with the system. Given these two datasets and access to a downstream task, we want to identify a minimal set of PVTs such that transforming the failing dataset with respect to these PVTs fixes them. To solve this problem, we propose DataPrism, which operates in 4 main steps. Let us go over these steps one by one. First, it identifies a set of discriminative PVTs, that is, the PVTs which are not the same in the failing and the passing datasets. For example, we calculate the PVTs for the passing datasets as shown here. Then we identify the PVTs of the failing dataset and calculate the intersection. We then remove the intersection of those and keep the remaining PVTs from the passing dataset. These PVTs are used for the analysis by subsequent stages of the pipeline. The second stage organizes the discriminative PVTs in the form of a bipartite graph. This bipartite graph consists of PVTs on one side and the attributes on the other side. A PVT is connected to an attribute A if the corresponding profile depends on that attribute A. For example, domain of age is connected to the attribute age in the graph shown here. The high-level intuition of constructing this graph is that attributes with incorrect format or mistakes generally have multiple discriminative PVTs. Therefore, the PVTs connected to these high-degree attributes in the graph are considered for intervention first as compared to other PVTs. And after constructing this graph, the third stage ranks shortlisted PVTs based on a benefit score. This score captures the likelihood that malfunction score would change if that particular profile is intervened. Specifically, the benefit of a PVT is the violation score of the failing dataset times the fraction of tuples that are transformed by the PVT's transformation. We show the benefit scores of different PVTs in this table. In the subsequent stage, highest scoring PVT, which is correlation between sex and income, is considered for intervention. The fourth stage of the pipeline is the intervention procedure, which applies the transformation and then runs the pipeline to calculate its malfunction score. In this example, breaking correlation between sex and income reduces the malfunction below 0.2, and therefore the pipeline stops after searching over other PVTs. As a last step, DataPrism also ensures that the solution set is minimal. And to test minimality, DataPrism removes one PVT at a time and keeps it only if it is necessary to reduce malfunction. Now, let us look at some of the evaluation results of DataPrism. We tested our approach on 6 different application domains spanning classification, entity linking, sentiment prediction, data integration, and data visualization. All these applications were tested on real-world datasets, and each pipeline failed due to a different cause of mismatch with the data. In terms of the baseline, there is no prior technique that exposes mismatch between data and systems. Therefore, we adapted state-of-the-art debugging and explainable AI techniques to explain the cause of mismatch. Specifically, we adapted BugDog, which is designed to debug pipeline implementations, and Anchors, which is a rule-based technique to explain ML models. In addition to these two baselines, we implemented a group testing-based approach to intervene multiple PVTs at a time simultaneously. Now let's look at the results with these techniques. Here we show the number of interventions required by each technique to expose the cause of malfunction. We observe that DataPrism is highly effective and requires the least number of interventions. Other baselines are not very effective. Even though group testing does not require a lot of interventions, it does not identify the true cause of malfunction in half of the cases. We further tested the effect of different parameters on the number of required interventions. We can observe that DataPrism requires the least number of interventions across all settings of these parameters, and the growth rate of interventions is sublinear in the number of discriminative PVTs. In summary, we studied a novel problem of exposing the disconnect between data and systems. We proposed DataPrism approach to explain the cause of malfunction in the form of data profiles, or PVTs to be more specific. Interventional approach of DataPrism helps to produce causally verified explanations. Empirical evaluation of DataPrism on various systems demonstrates its effectiveness to identify the ground truth cause of malfunction. And we also show that it requires the least number of interventions. Thank you.